Yeah,
Hello everyone.
now we are live.
Okay. Hello everyone. This is Prabal and here with me I have Akshat and Shreya from Society for Data Science, Birla Institute of Technology, Mesra. So in today's session we have with us Dr. Joshua Starmer. He doesn't really need an
Hey, Prabal,
introduction, but
Prabal.
for this, yeah.
Yeah, your voice was stammering a bit just due to some internet connectivity issues. Can you please do it again? Like,
Okay. Better now.
yeah,
Okay. So hello everyone.
yeah, you
This
can
is
begin.
Prabal. Yeah. And here with me I have Akshat and Shreya from Society for Data Science, BIT Mesra. So, in today's session, we have Dr. Joshua Starmer with us. He doesn't really need an introduction, but for the sake of doing it, let me introduce him to you guys. Dr. Joshua Starmer has been an assistant professor at Chapel Hill, University of North Carolina, and his stature comes from his visualization of statistical concepts. What makes studying with him an extraordinary affair is his sense of humor brought to science. To enthrall his audience, he plays ukulele openings for his videos as well as he sings professionally. As a machine learning champion, an early adopter, and expert, Dr. Joshua Thomas aims to enlighten individuals and organizations on the true significance of data and how to turn it into actionable insights and deployable situations. Over to you, sir.
Ha! Today we're gonna talk about neural networks. Today we're gonna look inside the black box. It's gonna be awesome. Hooray! Hey everybody, I'm Josh Starmer, and welcome to this seminar on neural networks. Let me just put my ukulele down. It'll probably fall over about halfway through the talk, but that is okay. Um, so let's get started. I'm going to share my screen with you. Here it is. So there we go. Today we're going to talk about neural networks part 1, inside the black box, and then we're going to talk about I'm actually going to do 2 parts of this series. I've got a series of videos on neural networks. Um, they're online. You can watch them. The advantage of being here live right now is I'm actually probably going to give you some extra insights, sort of behind the scenes things that happened while I was making the video but that didn't make it into the final cut. Um, and I think we're going to cover 2 parts of this series, and we'll just see how it goes. But we're going to start with part 1, inside the black box, and that'll give everyone a good frame of reference. Okay, so neural networks, one of the most popular algorithms in machine learning, cover a broad range of concepts and techniques. However, people call them a black box because it can be hard to can be hard to understand what they're doing. The goal of this series is to take a peek into the black box by breaking down each concept and technique into its components and walking through how they fit together step by step. In this first part, we'll learn about what neural networks do and how they do it. In part 2 of this series, I talk about back propagation, and basically that's how neural networks are fit to data. There's a lot of taking derivatives via the chain rule in back propagation. And then we'll talk about variations on the simple neural network presented in this part, including deep learning. So I've got some crazy awesome news. I have a new way to think about neural networks that will help beginners and seasoned experts alike gain a deep insight into what neural networks do. For example, most tutorials use cool looking but hard to understand graphs and fancy mathematical notation to represent neural networks. In contrast, I'm going to label every little thing in the neural network to make sure it's easy to keep track of the details. And the math will be as simple as possible while still being true to the algorithm. So we're going to use what looks like very, very simple math. We're just going to use some addition and some multiplication, basic stuff. But this is the actual math that drives neural networks. I'm not dumbing it down. This is actually what's going on. I'm just not obscuring it with fancy mathematical notation. So this is sort of like you look at a fancy car and you're like, oh, that's a very fancy looking car. But when you open the hood, it's got an engine just like every other car made of the same parts. There's nothing magical going on. And we're just going to look at the parts rather than the fancy stuff. These differences will help you develop a deep understanding of what neural networks actually do. So with that said, let's imagine we tested a drug that was designed to treat an illness. And we gave the drug to 3 different groups of people with 3 different dosages: low dosages, medium, and high dosages. The low dosages were not effective, so we set them to 0 on this graph. In contrast, the medium dosages were effective, so we set them to 1. And the high dosages were not effective, so we set those to 0. Now that we have this data, we would like to use it to predict whether or not a future dosage will be effective. However, we can't just fit a straight line to the data to make predictions. Because no matter how we rotate the straight line, it can only accurately predict 2 of the 3 dosages. The good news is that a neural network can fit a squiggle to the data. The green squiggle is close to 0 for low dosages, close to 1 for medium dosages, and close to 0 for high dosages. And even if we have a really complicated data set like this, a neural network can fit a squiggle to it. In this StatQuest, we're going to use this super simple data set and show how this neural network creates this green squiggle. But first, let's just talk about what a neural network is. A neural network consists of nodes, so these squares oftentimes these are represented as circles in a neural network. When you see a picture of a neural network, they have circles. I'm using squares. And the connections between the nodes. So the other part, the other most important part of a neural network are these edges that connect each node in the neural network. Note, the numbers along each connection represent parameter values that were estimated when this neural network was fit to the data. So when we had this data, when we fit it to the data, we estimated these parameters. For now, just know that these parameter estimates are analogous to the slope and intercept values that we solve for when we fit a straight line to data. So if we do linear regression or we use gradient descent or something like that, we can fit a line to data. And by doing that, we end up solving for the slope and the intercept. And what we're doing here is the exact same thing. With this neural network, we start with unknown parameter values that are estimated when we fit the neural network to a data set using a method called backpropagation. And I talk about how backpropagation estimates these parameters in part 2 in this series. But for now, just assume that we've already fit this neural network to this specific data set. And that means we already have estimated these parameters. Also, you may have noticed that some of the nodes have curved lines inside of them. These bent or curved lines are the building blocks for fitting a squiggle to data. The goal of this StatQuest is to show you how these identical curves can be reshaped by the parameter values and are then added together to get a green squiggle that fits the data. Note There are many common bent or curved lines that we can choose for a neural network. This specific curved line is called Soft Plus, which sounds like a brand of toilet paper. Alternatively, we could use this bent line called ReLU, which is short for Rectified Linear Unit and sounds like a robot. Or we could use a sigmoid shape or any other bent or curved line. Oh no, here's the terminology alert. The curved or bent lines are called activation functions. When you build a neural network, you have to decide which activation function or functions you want to use. When most people teach neural networks, they use the sigmoid or this S-shaped activation function. That's often what you see when you read a tutorial or you see a tutorial on YouTube. They'll show you how to build a neural network with a sigmoid activation function. However, in practice, it is much more common to use the ReLU activation function or the Soft Plus activation function. So we'll use the Soft Plus activation function in this StatQuest. Anyway, we'll talk more about how to choose activation functions later in this series. Note, this specific neural network is about as simple as they get. It only has one input node where we plug in the dosage, only one output node to tell us the predicted effectiveness, and only two nodes between the input and output nodes. However, in practice, neural networks are usually much fancier and have more than one input node, more than one output node, different layers of nodes between the input and output nodes, and a spider web of connections between each layer of nodes. Oh no, here's another terminology alert. The layers of nodes between the input and output nodes are called hidden layers. When you build a neural network, one of the first things you do is decide how many hidden layers you want and how many nodes go into each hidden layer. Although there are rules of thumb for making decisions about hidden layers, you essentially make a guess and see how well the neural network performs, adding more layers and nodes if needed. Now, even though this neural network looks fancy, it's still made from the exact same parts used in this simple neural network, which only has one hidden layer with two nodes. So let's learn how this neural network creates new shapes from the curved or bent lines in the hidden layer, and then adds them together to get a green squiggle that fits the data. Note, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. The first thing we're going to do is plug the lowest dosage, 0, into the neural network. Now, to get from the input node to the top node in the hidden layer, this connection multiplies the dosage by negative 34.4 and then adds 2.14. And the result is an x-axis coordinate for the activation function. For example, the lowest dosage, 0, is multiplied by negative 34.4, and then we add 2.14 to get 2.14 as the x-axis coordinate for the activation function. To get the corresponding y-axis value, we plug 2.14 into the activation function, which in this case is the Soft Plus function. Note, if we had chosen the sigmoid curve for the activation function, then we would plug 2.14 into the equation for the sigmoid curve. And if we had chosen the ReLU bent line for the activation function, then we would plug 2.14 into the ReLU equation. But since we are using soft plus for the activation function, we plug 2.14 into the soft plus equation. And the log of 1 plus e raised to the 2.14 is 2.25. Note, in statistics, machine learning, and most programming languages, the log function implies the natural log or the log base e. Anyway, the y-axis coordinate for the activation function is 2.25. So let's extend this y-axis up a little bit and put a blue dot at 2.25 for when dosage equals 0. Now, if we increase the dosage a little bit and plug in 0.1 into the input, boop, boop, the x-axis coordinate for the activation function is negative 1.3. And the corresponding y-axis value is 0.24, excuse me. The corresponding y-axis value is 0.24. So let's put a blue dot at 0.24 for when dosage equals 0.1. And if we continue to increase dosage values all the way to 1, which is the maximum dosage value, we get this blue curve. Note, before we move on, I want to point out that the full range of dosage values from 0 to 1 corresponds to this relatively narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, then we multiply them by negative 34.4 and add 2.14. And when we do that, we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values inside that red box are used to make this new blue curve. Bam! Now we scale the y-axis values on the blue curve by negative 1.3. For example, when dosage equals 0, the current y-axis coordinate for the blue curve is 2.25. So we multiply 2.25 by negative 1.3 and get negative 2.93. And negative 2.93 corresponds to this position on the y-axis. Likewise, we multiply all of the other y-axis coordinates on the blue curve by negative 1.30. And we end up with a new blue curve. Bam! Now let's focus on the connection from the input node to the bottom node in the hidden layer. However, this time we multiply the dosage by negative 2.52 instead of negative 34.4. And we add 1.29 instead of 2.14 to get an x-axis coordinate for the activation function. Remember, these values come from fitting the neural network to the data with backpropagation, and we'll talk about that in part 2 in this series. Now, if we plug the lowest dosage, 0, into the neural network, then the x-axis coordinate for the activation function is 1.29. Now we plug 1.29 into the activation function to get the corresponding y-axis value. We get 1.53. And that corresponds to this yellow dot. Now we just plug in dosage values from 0 to 1 to get the corresponding y-axis values. we get this orange curve. Note, just like before, I want to point out that the full range of dosage values from 0 to 1 corresponds to this narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in this red box are used to make the new orange curve. So we see that fitting a neural network to data gives us different parameter estimates on the connections, and that results in each node in the hidden layer using different portions of the activation functions to create new and exciting shapes. Now, I'm going to pause a little bit and I want to emphasize this point because I think it's the most important part of what neural networks do. You'll see that both activation functions are the same. Like the activation function itself, we're using soft plus in both nodes in the hidden layer, in the top node and the bottom node. They both have the soft plus activation function. However, given the same dosage values, going from 0 to 1 in this case, we only use the portion of the activation function in the top one. We use a sort of a wide portion of it, and we only use a very narrow, relatively narrow portion of that same exact activation function in the bottom one. We also, you'll notice that we end up multiplying these sort of curved fragments by positive numbers or negative numbers, and that flips them. And what we're doing right here is we're stretching or condensing them. And what we do, and this is how neural networks creates a wide variety of nonlinear shapes. And we'll see in a little bit that we add these shapes together to get even more exciting nonlinear shapes. But I just want to drive home this point that we've got this nonlinear thing, this soft plus curve. So it's not a line, it's this nice kind of gradual curve. And we are stretching it and flipping it to get new shapes and unique shapes that did not exist before. Now, just like before, we scale the y-axis coordinates on the orange curve, only this time we scale by a positive number, 2.28. So here we are scaling, boop, boop, boop. And that gives us this new orange curve. Now the neural network tells us to add the y-axis coordinates from the blue curve to the orange curve. So we just add the y-axis values, and that gives us this green squiggle. Then finally, we subtract 0.58 from the y-axis values on the green squiggle, and we have a green squiggle that fits the data. Bam! Now, if someone comes along and says they were taking dosage equals 0.5, then we can look at the corresponding y-axis coordinate on the green squiggle and see that the dosage will be effective. Or we can solve for the y-axis coordinate by plugging dosage equals 0.5 into the neural network and do the math. Boop, 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 boop. So we're just plugging in the number 0.5, just like we did for all of the other dosages earlier. Boop, boop, boop. Boop, 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 boop. So this is so small that we're just going to call it 0. And this is what we have is 0.71 times 0 times 2.28. Boop, boop. And so the efficacy of the drug is 1.03. Boop. And we see that the y-axis coordinate on the green squiggle is 1.03. And since 1.03 is closer to 1 than 0, we will conclude that dosage equals 0.5 is effective. Bam! Now, if you've made it this far, you may be wondering why this is called a neural network instead of a big fancy squiggle fitting machine. The reason is that way back in the 1940s and 50s, when neural networks were invented, they thought the nodes were vaguely like neurons, and the connections between the nodes were sort of like synapses. However, I think they should be called big, fancy, squiggle-fitting machines, BFSFMs, because that's what they do. Note, whether or not you call it a squiggle-fitting machine, the parameters that we multiply are called weights, and the parameters that we add are called biases. Note, this neural network starts with two identical activation functions, but the weights and biases on the connections slice them, flip them, and stretch them into new shapes that are then added together to get a squiggle that is entirely new. And the squiggle is then shifted to fit the data. Now, if we can create this green squiggle with just two nodes in a single hidden layer, just imagine what types of green squiggles we could fit with more hidden layers and more nodes in each hidden layer. In theory, neural networks can fit a green squiggle to just about any data set, no matter how complicated. And I think that's pretty cool. Triple bam. So that's the end of our first part. And what I'm going to do is we're going to skip ahead and we're going to talk about, the ukulele finally fell over. That was bound to happen. It always happens once per presentation. Now we're going to talk about, we're going to skip ahead to neural networks part 4, multiple inputs and outputs. Okay, so far the neural networks that we looked at have been super simple and only predict whether or not the dosage for a drug will be effective. The neural networks just have one input node and one output node. When there's only one input node, then the data we are using to make predictions, in this case, dosages, can all fit on the x-axis of this graph. In other words, the input is one-dimensional since it only needs one axis in the graph. Likewise, a single dimension, the y-axis, represents the output values. Combined, we get a two-dimensional graph with the input, dosage, on the x-axis and the output, drug effectiveness, on the y-axis. Because the input and output combine to form a two-dimensional graph, we can see how the weights and biases in this neural network slice, flip, and stretch the curved or bent activation functions into new shapes that are added together to make a two-dimensional squiggle or shape that fits the data. By the way, you'll notice that in this neural network, we're using the ReLU activation function. So it's just a bent line. And that's why when we're making these new shapes, they're kind of bent or they're straight lines. And what the ReLU activation function does is whatever the x-axis coordinate is, if that axis coordinate is negative, then it sets the output value is 0. So what we're seeing here is you see that point on the green line on the left-hand side where the X is. That's a negative value on that on the axis. So the input to the ReLU is a negative value, and so ReLU sets it to 0. However, this point right here is positive. It's above 0, and so ReLU just outputs the raw input value. So the ReLU is either whatever the input value is the output, or 0 if that input is less than 0. Here we are, we're back to input values being less than 0, and so they're set to 0. And we end up with this kind of pointy shape, which is actually a better fit to the data than before. And the ReLU activation function is probably the most popular activation function of all. It's the one used in deep learning and what do we call that? Image recognition and image classification. So bam. Now let's look at a more complicated neural network that has more than one input node, more than one output node. Now this neural network may look really fancy, but all it does is take two measurements from an iris flower, the width of a petal, which is this part of the flower, and the width of the sepal, which is this part of the flower. And with that information, it predicts the species, either Setosa, versicolor, or virginica. Now, raise your hand if you already knew that this was a sepal and not a petal. Not me. I thought they were all petals. So I learned something when I did this. Anyway, to keep things simple at the start, let's begin with both input nodes, but just one output node for Setosa. Later on, we'll add the other two output nodes. But for now, let's just keep things simple and just use one output node. Now let's see what happens when we plug values for petal width and sepal width into this simplified neural network. Since we have two inputs and one output, if we are going to draw a graph of what's going on, then we need a three-dimensional graph. The inputs, petal width and sepal width, each get an axis. And the output, the prediction for Setosa, gets the y-axis. Note, to keep the math simple, I scaled the inputs to be between 0 for the smallest value and 1 for the largest value. So let's start in this corner where petal and sepal width equals 0 and plug those values into the neural network. First, let's determine the x-axis coordinate for the top node in the hidden layer. We multiply the petal width by the weight associated with its connection to the top node in the hidden layer, -2.5, and we multiply the sepal width by the weight associated with its connection to the top node in the hidden layer, 0.6. And we add the two terms together and add the bias, 1.6. And that gives us the x-axis coordinate for the activation function, which is 1.6. Now we plug 1.6 into the ReLU activation function and get the y-axis coordinate 1.6. And remember, the ReLU activation function just takes the maximum value of either the input or 0. And if the input is greater than 0, it outputs the input value. Otherwise, it outputs 0. So in this case, we got 1.6 because 1.6 is greater than 0. And 1.6 corresponds to this blue point on the graph when petal and sepal widths are both 0. Now let's increase petal width to 0.2, but keep sepal width at 0. Now when we do the math, we get 1.1 for the x-axis coordinate and 1.1 for the y-axis coordinate. And 1.1 corresponds to this blue point on the graph. Likewise, when we increase petal width to the maximum value, 1, but keep sepal width at 0, we get these blue dots. Now let's increase sepal width to 0.2 and run values for petal width from 0 to 1 through the neural network. Likewise, if we keep increasing sepal width to 1 for different values of petal width, we get this blue surface. Actually, not just a blue surface, it's a blue bent surface. The bend corresponds to the points where the ReLU activation function set the y-axis values to 0. Now we multiply the y-axis value for each point by negative 0.1. For example, the original y-axis value for this point, when petal and sepal widths are both 0, is 1.6. And 1.6 times negative 0.1 equals negative 0.16. So the final point is here, just below 0. Likewise, when we multiply all of the other y-axis coordinates by negative 0.1, we get this final blue bent surface. Now we do the exact same thing for the connections to the bottom node in the hidden layer. Boop, 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 boop. And we end up with this orange bent surface, where the bend occurs where the ReLU activation functions set the y-axis values to 0. Then we multiply each y-axis coordinate by 1.5 to get the final orange bent surface. Now we add the y-axis coordinates on the blue bent surface to the y-axis coordinates on the orange bent surface. For example, the y-axis coordinate for this blue point is negative 0.16, and we add the y-axis coordinate for this orange point, 1.05. To get 0.89, the y-axis coordinate for this green point. Anyways, we do that for every single point, and ultimately, we end up with this green crinkled surface. Now, the last thing we do is add the final bias, 0, to each y-axis coordinate. And since adding 0 doesn't change the green crinkled surface, this is the output for setosa. Bam! Looking at the green crinkled surface, we see that the value for setosa is highest when the petal width is close to 0. And the value for setosa is lowest when the petal width is close to 1. Note, remember that we scaled the inputs to be between 0 and 1. Thus, petal width equals 0 does not imply that the petal is 0 centimeters wide. Instead, 0 refers to the smallest width in the training data set. Likewise, 1 means the largest width in the training data set. Small bam. Now, to review the concepts so far. When we have two inputs, the neural network creates curved or bent surfaces that are added together to make a new crinkled surface that, in this case, we can use to make predictions about whether or not the species of an iris is setosa. For example, if we found this iris while walking in the woods and the scaled petal width was 0.5 and the scaled sepal width was 0.37, then we could look at the y-axis value on the green crinkled surface that corresponds to these measurements and see that this particular iris is probably not setosa because the y-axis value is closer to 0 than 1. And this is confirmed when we run the numbers through the neural network and get 0.09. Bam. Now that we have a green crinkled surface for setosa, let's determine the output for the second species, versicolor. Just like before, we start with the connections to the top node in the hidden layer. And because the weights and biases are the same as before, we start it with the same blue bent surface. However, because we will multiply the y-axis coordinates by 2.4, let's change the range of the y-axis from 0 to 2 to negative 6 to 6. So we're just stretching out the y-axis range. Bam. Now, multiplying the y-axis coordinates by 2.4 gives us this final blue bent surface. Now we create the orange bent surface from the bottom node in the hidden layer. and multiply the y-axis coordinates on the orange bent surface by negative 5.2. Now we add the y-axis coordinates from the two bent surfaces together to create this red crinkled surface. Lastly, we add the final bias, which is 0, to the y-axis coordinates on the red crinkled surface, and that gives us the final surface for predicting if the iris species is versicolor. Now, I'll admit, it's hard to see what values for petal or sepal widths will give versicolor a high score on this red crinkled surface. But when you change the y-axis scale from -6 to 6 to -0.5 to 1, we see that when petal width is close to 0.4, we will get a high value for versicolor. Double bam! Now, just like we did for setosa and versicolor, let's determine the crinkled surface for virginica. Just like before, we start with the blue bent surface from the top node in the hidden layer. But now we multiply the y-axis coordinates by -2.2. And just like before, we create the orange bent surface from the bottom node in the hidden layer. But now we multiply the y-axis coordinates by 3.7. Now we add the y-axis coordinates from the two bent surfaces together to get this purple crinkled surface. Lastly, we add the final bias, 1, to the y-axis coordinates on the purple crinkled surface. And that gives us the final surface for predicting if the iris species is virginica. Now, so we can see what's going on, let's change the scale for the y-axis from -6 to 6 to 0 to 1. Now we see that when petal width is close to 1, the widest, then we will get a high score for virginica. Triple bam! At long last, we have crinkled surfaces for setosa, versicolor, and virginica. So now we can plug in the petal and sepal widths from the iris that we found and run the numbers through the neural network and predict that this iris is versicolor because that output value, 0.86, is closest to 1. Bam! Now, that said, usually when there are 2 or more output nodes, the output values are sent to either something called argmax or something called softmax before a final decision is made. And I'll talk about argmax and softmax in the next StatQuest in the series. In fact, that's already online. So if you guys want to learn more about argmax and softmax, you can check that out online. You can also check out how backpropagation works. So how do we estimate these weights and biases in the neural network? That's also available online. So that is the end of my talk today. I am perfectly willing to take questions from anybody if you have any questions. So let me know.
Thank you, sir. It was really an informative session. So
Thank
we
you.
indeed have some questions from some of our audience. And so the
Fantastic.
first question is, why do we generally use ReLU function instead of sigmoid or even tanh for making activation functions?
So one reason is the math for ReLU is super easy, right? We just compare it to 0, and if it's less than 0, we set it to 0. Otherwise, we output the exact same value. So the math is straightforward. The derivative of the ReLU function, which is what we need to do in order to optimize the parameters and weights, we use gradient descent. And so we take a derivative of that function. Although the derivative is not defined at 0 because it's a bent line, it's just like that. Although the derivative is not defined at that point, the derivative of the angled part is 1, and the derivative of the flat part is 0. And because the probability of getting something to be exactly 0 is very small, we can just define the derivative at that point, at that undefined location. We can just define that to be 1 or 0. It doesn't matter. We'll get the same results. And so using that derivative of 1 or 0 makes the math super easy. So that's one thing that makes the RailU very popular. It also because the derivatives are also very, this is derivative is 1 and this is 0. With the sigmoid curve, we've got a shape like this, like a sigmoid shape, and the derivatives out on those edges are never 0, but are often very close to 0. And that makes gradient descent tricky when you have a derivative out on the edge of that sigmoid shape, because if you're familiar with gradient descent, we take the derivative and we use that derivative to make a step size, and that step size determines how quickly we move towards the optimal value. Now, when we're far from the optimal value because we're out on these edges, actually, I don't know. If we're out on those edges, the derivative is super, super, super small. It's very, very close to 0. And that means we're going to take very, very small steps towards the optimal value. And they call that the vanishing gradient problem, because the derivative is so small that we're just taking such tiny steps that we fail to converge on the optimal value. And that's a problem that the RailU doesn't have to deal with. It has a different problem, which in some situations isn't actually thought of as a problem. So it's possible that all of the inputs into a RailU activation function can be 0, or can be less than 0. It could be that all of the inputs are less than 0. And if that is the case, then the output of that RailU function will always be 0. It'll just be that straight line, right? Not very interesting. That's not a nonlinear shape that we can add together in interesting ways. So that is a problem. However, it's not typically thought of as a major problem because usually we have enough other nodes in the hidden layer. Like in the ones I have, we just have 2 nodes because I want to keep it simple. But oftentimes we might have a bunch more nodes. And so if some of them go black, they just end up being 0s. It's okay. The rest of them will compensate. It's also somewhat rare to have every single input to be less than 0 because usually we have a relatively large data set. And one of those values, one of them will end up being above 0. And that'll keep that hidden node alive. So that was a very long and drawn out answer. But I hope that answered your question about why we generally use the RailU instead of the sigmoid.
Yes, sir. It was a very detailed answer. So he must have got what he was asking for.
I hope so.
We have comment, we have comment from Julia Schaffer. Seen the Iris dataset 100 times, but never got to know what's happened.
Yeah, isn't that hilarious? So, I think that's hilarious too, because I've seen that. If you do data science and especially if you work with R, I feel like every single example is the Iris data set. And so we all know it so well, but I never knew that a sepal and a petal were different things. So I think it's hilarious too. I will say one thing about this data set. Because it's used so many times, I've actually tried to avoid, in my StatQuest videos in general, I typically try to avoid using these standard data science data sets like the Iris data set. I try to avoid those because we've seen them so many times that we kind of stop seeing them. It's like, oh, it's Iris, blah, blah. We kind of know what we're going to get. And it's like, it's hard for me to even really focus on what's going on just because I'm kind of bored with the data. I'm like, that's boring.
It's like cringy stuff.
Yeah, exactly. However, in this case, I have a friend who lives in Svalbard, Norway, and he requested it. And to be honest, at first I was really resistant to it, but once I started working with this specific data set, it ended up being perfect for illustrating how sort of multiple inputs and outputs work in a really simple way. And it just worked great. And I ended up being really pleased. And I ended up learning that sepal and pedal widths were different things. So I ended up being really pleased with myself, even though it's kind of a generic data set we've all seen maybe too many times at this point. I ended up having a lot of fun using it with this StatQuest. So,
Yeah,
any other questions?
that's really the case. Yeah,
Yeah.
we have another question
Oh
from
wow.
Shivam. How can we prove that these squiggle fitting machines can approximate any function? So the title given by you is becoming popular now.
Yeah.
Squiggle fitting
Yeah. So
machines.
that's a great question. And unfortunately, I'm not a mathematician, so I can't give you a proof. However, I can give you intuition. And the intuition is, we ended up fitting some pretty interesting squiggles with just two hidden nodes in a single hidden layer with two nodes in that layer. Now, and that was just, relatively simple shapes we were adding together. Now, imagine if we had 10 times that many, if we had 20 nodes in that hidden layer, and imagine we had 10 hidden layers. And each one we're using different parts and we're flipping and we're stretching it in new ways. So that's not a proof that we can fit or approximate any function, no matter how squiggly. But it's just intuition. It's kind of the best I can do. Unfortunately, I'm not a mathematician, and I'm not really good with proofs like that off the top of my head. But just have some intuition. One thing that is interesting, though, and this is mildly related to the question, is in the neural networks that I showed you in this video, or this stream. I guess it's not a video yet. It will be soon. The neural networks that I showed you in this stream are very simple. Really, they're two-dimensional total. We got one dimension for input and one dimension for output, or we had two dimensions for input and one dimension for output. And so we could actually look and see what the output function was, what the neural network fit to the data. What I think is interesting is once we end up with more inputs and possibly more, well, it's actually just down to more inputs. We can't plot it anymore. We can't look at it. We just have to look at the output and see what the mean squared error is, or there's this other thing called cross entropy, which is basically, it's another metric of how well we're fitting. And we can say, oh, this neural network fits the data better than this other one, but we don't actually know how it's fitting. And if you have just a second, I want to illustrate this.
Yeah, sure. So you can.
I want to show
it.
you why this is kind of a weird thing. And we'll go back to that first one. Give me a second. Let's go back to neural networks main ideas, and let's pull that up. Let's look at.
So you have not shared a screen yet, so we can't.
Not yet. I know. I'm finding the right. I'm finding what I want to share.
Okay. Yeah. Not a problem.
And I'm just babbling in the background. Yeah. So let's go with this window. So play. And now let's share screen. Sorry, you had to wait for this, but I want to show you something. So check this out. I don't know how well you can see the data. The data are these circles. We're looking at the graph on the left-hand side. So we got a green squiggle fit to the data. Now you'll notice that the green squiggle kind of like shoots up pretty high to the left of the data that's effective, right? And then it actually starts, it comes down in a nice kind of way that we would expect. What I think is interesting is the in between the data. So we've got a bunch of values at 0 for low dosages. And then we have a bunch of values at or close to 0.5 that are effective. And the y-axis value for those is 1. Now, what I think is interesting is in between those low dosages and the medium dosages, that squiggle goes straight up and it goes to positive, 1.2 or something, 1.3. And in this case, it's okay. But imagine if someone came in with a dosage that was intermediate between low and medium, like they had a semi-medium, semi-low dosage. So it's in between. What we would think that this curve would have a nice kind of gradual bell shape fit to the data, but instead it's got this weird shape, and it's not necessarily what we would expect. And so I think it's important to know that the neural network will fit the training data, but for the values in between the training data, like those intermediate values, like a dosage that isn't quite medium, isn't quite low, it's that in between space, we don't really know what to expect. And the neural network doesn't guarantee that it's going to give us sort of like, well, the most obvious sort of like an intermediate value. It might give us a value that says it's super effective, and it's just because it never had data in the training data set to correct that error if it is an error, you know. And so I think it's important to know that because we can't see these functions, once we have multiple inputs and outputs, we can't actually see how it fits. It's sort of like it's kind of a little freaky that we don't actually know how it's going to perform on these intermediate input values. So that's all I wanted to say with that. So we'll stop sharing and go back to jibber jabber. Anyways, any more questions? We probably have time for one more.
Okay, so you have time for one more, so we can move this.
Okay.
With a question from Mr. Tripathi. Now it seems that tensor analysis can be very useful for someone who wants to go into deep and wants to know about its working.
Yeah. So TensorFlow and all those things are ways of representing the math. I could be totally wrong about this, actually. I don't know a lot about tensors. But what I think of tensors are as, you know, imagine you've got a matrix of numbers. A tensor is kind of a multi-dimensional.
Basically a matrix of collection of matrices and matrices. And that's what tensors are. It's just a fancy term for matrices.
Exactly. A collection of matrices. Yeah. And that when we actually do neural networks, we do it, because the mathematics is simply addition and multiplication. Those are what we call linear operators, which are the domain of something called linear algebra. And linear algebra has ways of very efficiently doing these multiplications and additions in a very kind of compact way, and using matrices and using tensors to kind of store the data in a way that we can efficiently process it. So the idea behind sort of tensors and using tensors is a way to sort of optimize the mathematics that goes on behind the scenes when we make neural networks. And yeah, so hopefully soon I'll do a cover on sort of like what tensors are doing. We'd probably have to dive into some linear algebra to get into kind of the nuts and bolts of sort of how linear algebra does the mathematics of neural networks. But that's something I could do. And especially since it's a very popular thing right now.
Yes, sir. So that was the last question for the day. And let's conclude, because we all know time is very expensive. So let's conclude the session by your song. So can you please sing a song for us and our audience?
Thank you. Thank you for paying attention to me for a solid hour. Thank you. And goodbye for now. Come back and watch my videos. I really appreciate it. StatQuest.
Yeah. And double bam.
Double bam.
So yeah, right. Now Shreya will conclude the session. So Shreya, please conclude the session.
Yeah.
Thank you so much, sir, for enlightening us with your knowledge. And I, on behalf of everyone who has joined this session today, could say that this was definitely the best session ever on this summit. And as one of our viewers just commented there, that the way you explain neural network, it makes neural network as simple as linear regression.
Hooray! Hooray!
We certainly want to stay more, but we understand the time constraints. So we would be concluding today's session. And thank you everyone who has joined us today.
Yes, thank you.
Thank you, sir.